All right, so yesterday we were on lesson 22B, and we were working with this graph where let's go from day 0 up to day, say 600. And our number of cancer cells starts out at 20. So if we went from 0 up to, say, 1,000, let's see what happens over that period. Looks like we don't need to go up to 1,000. If we went up to 300, that would be far enough. So if we go up to 300, kind of, oops, you can't see that. Kind of function that we have here. What are the two ways that you know it's exponential? Way one.
It's not a straight line.
The graph is curving up. This is exponential growth. Remember, exponential decay would be a ski slope going the other direction, right? Horizontal asymptote at 0. But how can we tell from the formula or from the function that it's exponential? The variable is in the exponent, right? Okay. I thought that it did derivatives, but it doesn't. Okay, so then we have to do page 304, the a of t function. A of t is going to be a fraction. Well, we don't need the fraction because our denominator is 1. So it's going to be this function here. But the difference is the numerator here is going to be t plus 1. So what we've got here is this function here, f of t plus 1, minus f of t. Now if you notice, it graphs it as a blue line, but that blue line appears to be staying at 0. Well, the reason is each day the number of cancer cells doesn't grow by very much. So if we made the y-axis go from, let's say, 0 up to, say, 1 cancer cell per day, I don't know if that would be enough or not. Looks like it. So over the course of time, what do you notice about that exponential growth function that we had, the red function, compared to its slope function? It also is an exponential function. So let's, in our notes, let's write that down because that's an important thing to consider. 22B. If f of t is an exponential growth function, a of t, remember a of t is the average rate of change function, is an exponential growth function. Okay? Now, let's compare that to the one that we were doing in the previous lesson, where we didn't have exponential growth. we had exponential decay. So in these cases, if you recall, this is, I can't remember what it was. Oh, that's lesson 21. We didn't do 21. Let's go back to, well, anyway, you can see that the decay function, so if f of t, is exponential decay, recall that our slope started really negative, got less negative, got less negative, got less negative, until it was close to 0, correct? So here is the a of t function if this is f of t. So if f of t is an exponential decay, then a of t is negative exponential growth. Now, what do I mean by negative exponential growth? It's growing, right? But it's always negative. So negative exponential growth. (22) Caffeine. Probably a good subject to discuss in a math class that meets at 9 o'clock in the morning. By the way, this is the first semester that it's ever met at 9 o'clock. Other semesters it always met at 8 o'clock.
Oh, thank God. Really cried. What's fun? Yeah, actually. It's like this is already a block class.
So, yeah, I had a meeting yesterday at 7:30, and I got to the corner, and there were some kids getting onto the bus because their school starts at 7:30. And I was like, wow, can you imagine? They were junior high kids. They were getting onto the bus at like 6:45. Just think what time they had to get up in the morning. Like, what, 6 o'clock?
And then the bus would be there at 6:30.
Isn't that something?
7:55 or something.
So, if you take a college class that meets at 9 o'clock, you can pretty much say, quit your complaining, right? Okay. Caffeine is eliminated in the bloodstream of a non-smoking adult at the rate of 16% per hour. For adults who smoke, caffeine is eliminated from the bloodstream at a rate of 25% per hour. Suppose that a non-smoking adult drinks a small cup of coffee that contains 80 milligrams of caffeine. An adult who smokes drinks a larger cup that contains 120. Question 1, do you think that the smoker will always have more caffeine in his bloodstream than the non-smoker? Since it starts higher, always have more. Probably not, right? Okay? And that's what we're going to find out in this lesson. Down at the bottom of the page, it says, suppose that Mark is a smoker, Bob is a non-smoker. To model, assume that Mark drank a coffee containing 120 milligrams. Bob drank one containing 80 milligrams. Use the information to find a formula for the amount of caffeine remaining in each after T hours. Okay, I will get you started, but that's all I'm going to do. You have to work with your buddies in the class to get this, to complete this formula. Okay, we've got Mark, smoker, and smokers, if you recall, 25% per hour. Bob, non-smoker, 16% per hour, 120 here, 80 milligrams here. So we're going to have Mark as a function of time. So I suppose we could say Mark sub C for caffeine as a function of time, and B of T as a function of time. Go. I'll walk around and help. You should be able to do this by now. Oh, I should ask. 5, 4, 3, 2, 1. How comfortable are you coming up with a formula? 1, 2, 3, 5. Menominee. See some fingers. Not a clue. 4. Uh-oh. No fingers? Laura, how you doing?
I can't even read that says 255 light.
25% per hour. It's in your book.
Okay. I just is it 305?
Yep. Jess, getting them? It's absolutely crucial that you do these. Absolutely crucial. Yesterday, one of the students in a different class came up to me and said, "Can you help me figure out how to pass this class?" Well, and so we had a really good discussion. It went on after class was over, about the importance of test grades and stuff like that. But one of the things that I've been struggling with is my desire to help you pass, modeled against my desire to let you make your own decisions in life. And that's not easy. I'd love it if everybody would come to class because they want to, but I'm not going to punish people for not coming to class. I'd love it if people would take perfect notes on what happens in class. That would definitely help them pass the test. Like, for instance, that question on turning points on the test, that appeared in our notes, believe it or not.
I know, because I wrote it down.
Might not have been in this book. Nope, it was in the previous notebook. The number of turning points in a polynomial function
Oh, I got it in here.
was in the notes. Okay, let's do it. So, how do we translate the 120 and the 80 into our formulas? Those are the beginning values. We cannot put 25% in here because we don't care how much leaves, we care how much is left. So, this one will be 120 times what?
25.
Nope. 0.75
Excuse me.
to the t. This one will be 80 times 0.84 to the t. Now, 5, 4, 3, 2, 1 on how much you understand about how to write the formulas. Got it. Good. Let's graph them. Why is it important to graph them in this case? Well, it'll help us answer that very first question about, oops, that's not the guy. This is the guy. Bob and, what's the other guy's name? Mark? Yeah, Bob and Mark. So if you notice, Bob, now when you click on the graph, it gives you some important points. When you click on the other graph, it gives you some important points. What are the important points in an exponential function? The place where you cross the y-axis. Why is that an important point? Because it's part of the formula, right? But why does it give you the address right here? And which means
They're equal.
Which means that at 3.5 hours, even though Mark started with more caffeine, he's got less after that. Anybody know people who smoke? What is the relationship between them and caffeine? I had a buddy that I worked with. What was his name? Can't remember, but he drank a case of Diet Coke every day, and he smoked pack a day at
Is
least.
this person still living?
I don't know. I haven't seen him for years.
It's probably.
But why did he have to drink so much caffeine? Because caffeine is eliminated quickly in a smoker's bloodstream. Okay? So, to me, my image, and it may be a false image, of smokers is they always have a cup of coffee. Anybody disagree with that?
My friend's mom smokes and she doesn't drink coffee.
She doesn't drink coffee at
But
all.
she drinks a lot of pop. I don't know what.
Caffeine, a caffeine delivery system.
Yeah.
Jess, what were you going to say? Is that true?
Yeah, because they drink like a ton of coffee and
It doesn't affect them, right? Well, what do you mean when you say it doesn't affect them? Well, it wears off so quickly, it's almost as if they, right?
Is that like just with smokers, or is it with like people who chew too?
Oh, that's a good question. That'd be a good extra credit. I'll give you one.
Oh, really?
Yeah,
I'll
give
find
you
it
an
out,
extra
yeah.
credit.
Just for you.
I'll give you one for that. Okay. Then it says, sketch the graph of these functions on the same viewing window. So we've got a blue line. I don't have my blue marker anymore. I'll have to just use red. And I'll use green instead of blue. Okay. So I sketched those two graphs. And is Mark's caffeine level always greater than Bob's? No, because after 3 hours, they cross. D, suppose Kevin, a non-smoker, joins them, and he has 100 milligrams of caffeine at the same time. So K sub C of T is
Wait, what time? What? Point?
page 306, right here in the middle. Kc of T is, I see Eric's already filling it in. Eric, what numbers are you putting in?
100 times 0.84.
No, where did the point, I can see where the 100 came from. Why did you use 0.84? Because he's a non-smoker. So if we put that onto our graph, K of T, notice everywhere along the way, K is going to be higher than T. I'm going to go out here a ways and zoom in, just so that we can see. I hate that when it does that. If you notice here, K is always higher than M, or I'm sorry, than B. Why is that? Because he started with more. He will always have more in his bloodstream, and the amount will get closer and closer together as you go farther along, right? Page 306. An average adult notices the effects of caffeine when there is at least 30 milligrams present in their bloodstream. How do you notice caffeine? What's that?
That's not even a cup of coffee.
But how do you notice caffeine?
I don't know. Heart rate increases?
Heart rate increases, you stay awake, you get jittery. I don't know. Okay? So it says Mark has 30 after 4 hours. Mark has 30 after 5.6 hours, and Kevin has it 30 still at 6.9 hours. So, if you are going to exponential, let's see, what does it say? Use the graph to estimate how long it takes for each of them to drop below 30. So we'll just put them in here. 30 was at 4.8 hours, 5.6 hours, and 6.9 hours. Now, it is important that we realize that has to be a horizontal, right? Because it's talking about a level of caffeine. This is the caffeine axis. So it's going to be the amount of time with that amount of caffeine in your bloodstream. Next one. Generalization. F of x equals c a to the x. This is the base. This is the initial value. And the exponent is the variable. It says, let's use 10 as our C value. A. If A is greater than 1, give me a number greater than 1.
5.
So what we're going to do is we're going to say, how long does it take for our 10 to quintuple, right? 5 times as big, okay? When we graph that, we see that if it starts out at 10, after 1, how high up will we be? 5 to the first times 10. So after 1, we will already be way up there. What's going to happen after 2? That number is going to quintuple, right? So if our value is greater than 1, we say it is an exponential growth, okay? The key to it being greater than 1 is, the key to it being exponential growth if A is greater than 1. Okay? For example, is the graph increasing or decreasing? What do we notice? Increasing. What are the vertical and horizontal asymptotes? Horizontal asymptote at y equals 10, correct? Not asymptote, intercept. Asymptotes. What line won't this cross? We go backwards. Our horizontal asymptote is at y equals 0. Page 307. Suppose that we have a number, suppose that A is greater than B, which is greater than 1. So now we're going to put another number on here. Let's choose a different number that you can raise to the x power. Give me one. 4. So when we graph this one, what points is it going to go through? This point here, correct? 0, 10. But then over here, where is it going to go through? If you go over 1, it will only go up 40, right? Because it only goes up, it's not a quintuple event, it's a quadruple. It quadruples in size. So if B is less than A, the only thing that changes is B grows slower. They still exponentially grow. B grows slower. Next one. Suppose A is between 0 and 1. F of x equals 10. Remember that first number has to be 10. Give me a number for A.
7.
Pardon?
7.
That's not between 0 and 1.
0.5.
0.5, a nice easy number to use. Why is that an easy number to use? Because we can use the words half. Usually when we use the word half, we say half-life, right? They don't talk about radioactive third life, but if they did, it would be 1/3. We're doing 1/2. Okay, let's draw the graph. What point is it going to go through? Over 0, up 10, correct? By the time we get over here to 1, how tall is it going to be? Over 1, how high up will it be? Half as high, right? So our graph here is going to be and what's true about this? It's always decreasing. It's decay, right? It's decay if A is between 0 and 1. Let's choose a different value besides 0.5. Give me another value that we could have had. Oops.
0.25.
Okay, so that would be exponential quarter life, right? 0.25 to the x. So everybody agree it's going to go through over 0 up 10. But by the time we get to 1, where's it going to be? A quarter of that, right? Which would be over 1 up 2.5. Makes sense? So our graph is going to be like that. If B is less than A, but they're between 0 and 1, B decreases faster. The slope of B increases from negative infinity to 0, right? The slope starts out really, really, really steep, and it gradually gets closer and closer to 0. Next one. F of x equals 10 times 1 to the x. Okay, so this one sloped up, this one sloped down. What's going to be true about this graph? It's going to go through 10 and just keep on going. How does that work? Okay, I put some money into the bank. I put $10 into the bank. It earns 0% interest. How much will I have a year later? 10. 2 years later, 10. 3 years later, 10. 4 years later, 10. Got it? Last one says, if. Why is it difficult to have f of x equal 10 times let's say times negative 3 to the x? Let's just make a table of values here. X is 0, x is 1, x is 2, x is negative 2, x is negative 3. Let's just fill in that table of values. So what will our value be? Well, at 0, we're up 10. We already know that. But what's going to be true at 1? 1, the negative 3 to the first is negative 3 times 10 is negative 30. Right? Nope. Yeah. Negative 3 squared is positive 9. Right? Which will be 90. Negative 3 to the negative 2 is the same as 1 over negative 3 squared. Negative 3 squared is 9. So it'd be 10 over 9. This would be 10 over negative 27. So when we tried to graph it, we know this point is here. We know that over 1 we're down 30. Over 2 we're up 90. Back 1 we're down, or we're up 1/10. Back 3 we're down 1/27 or 1/3. So how can that be? I mean, it's not going to be. And what happens if it's negative, or if it's 2.3? Is it positive or negative? So try it and see. Let's see what our calculator says if you take negative 2 to the 2.3. Parentheses, negative 2, close parentheses, to the negative 3. Okay? Negative 2 to the negative 3.1. See what it says? It says negative 0.1109208883 plus 0.3, and then at the end of that it says I. I stands for, nobody's ever taken complex numbers? Imaginary number. So it's an imaginary number. It's not, you can't even graph it. Page 309. Newton's law of cooling. And there it is.
The coffee experiment. If you notice the red, we're doing an experiment with Newton's law of cooling. What we're going to be doing here is, let's suppose that we couldn't drink our coffee for 5 minutes. Should we add the cream first, or should we add the cream at the end? Newton's law of cooling explains which is better, and I'll explain why when we're done with the experiment.
Okay, so you understand the experiment. You want to have hot coffee. You have two choices. Add the cream right away. You can't drink your coffee for 5 minutes. I don't know, maybe you got called to a phone or something. Do you add the cream right away, or do you wait and add the cream just before you drink it? So those are the only two votes that you can make. Everybody understand the problem? Anybody have an idea that like they know for sure they're right?
Well, I already know because I saw this last. You showed us this in intermediate.
Did I really?
Mm-hmm. That's why I know.
Oh, okay.
If you add it right away, it'll dissolve better, but it would be colder later.
Okay. Menominee. What do they tell you about heating your house? You save energy if...
Put plastic on your windows?
If that's true. Temperature-wise. What?
Keep it at a constant temperature.
Keep it at a constant temperature, and the lower that constant temperature is, the more you save. Okay? And it has to do with Newton's law of cooling, but let's watch the video and see why. I didn't realize that I showed you this in intermediate algebra.
So let's get started. We're
Can't
going to
remember
put
why I
equal
would've.
parts
Must
of
have had it.
coffee into each of these two coffee
Newton's law of
cups.
cooling.
And we're going to measure their temperature over the course of the next 5 minutes and determine in which case the coffee stays warmer. Add the cream to 1, and let's start our experiment. Here we go.
Okay, now, how can you tell from the graph that it's exponential growth or decay?
I'm going to stir the coffee
Did
just
you
to
notice
make
it
sure
went
it's all the same
down?
temperature.
It was exponential decay.
While the experiment is running, we're going to go and cut the strawberry pie so that we can have dessert with our coffee. We'll be back in 5 minutes. So we've got the pie all cut. It's almost time to run our experiment. We just have to wait for our 300 seconds, and then we will dump the cream in, and then we'll eat our pie. Well, we've got 294 seconds. When we get to 300, it's time to pop. And here we go. So we add the cream. And if you notice, the temperature
So here's where we added the cream.
adding the cream later is slightly lower, just slightly lower than the temperature that it would have been had we added first. Here's the explanation. Newton's law of cooling states that the temperature gradually returns to the equilibrium temperature. If you notice on the graph, it shows that the temperature, the ambient temperature here in the room is about 17 Celsius, about 58, 63 Fahrenheit. A little chilly, but that's why we've got a sweater on. I think it's now time for us to have our pie. I'm going to stop the experiment and eat the pie. Now, turns out my wife doesn't want her piece of pie, so you know what that means. More pie for me.
Okay, here we go. Let's graph the important things in Newton's law of cooling. The first one I'm going to put on is this right here, and I'm going to call it room temperature. In our book, it talks about pizza. So I'm going to make pizza here in red. I'm going to make coffee in green. Now, pizza, it said, started out at 450 degrees. Coffee, let's say it starts out, I don't know, 180 degrees. And room temperature, let's say, is 70 degrees. Here is the graph for coffee. Here's the graph for pizza. Would you agree that even if the pizza were the same temperature as the coffee, the pizza would cool much more rapidly than the coffee does? Is there anybody that knows why coffee cools slower than pizza? Water stores a lot of heat. So the more water something it has in it, the longer it will store heat. Okay? So if you have pizza versus a piece of toast, they both just got done. Okay? Ooh, that's hot. I have to wait till it cools. Well, pizza is going to take much longer to cool than a piece of toast, right? By the time you put your toast on the plate, maybe spread a little butter on it, stuff's already like cooled off. Everybody agree? Why does pizza, which part of the pizza takes a long time to cool? The sauce and the cheese. They both contain a lot of water. Everybody agree with that? Okay. Newton not only had a law of what?
Oh, nothing.
Newton not only had a law of cooling, Newton had a law of heating. And to get the law of heating in, I'm going to put room temperature of 70 degrees up here rather than down there. Now, why? I mean, you can tell this is cooling because the temperature is going down until it gets closer to zero, right? And room temperature, right? Over here, I've got the purple line still at 70, but how do I know it's Newton's law of heating? Because I'm trying to get something up to room temperature, okay? Now, is that graph going to, well, how's that graph going to be shaped if it goes up to room temperature? Well, we probably aren't going to have like Just trying to think of something we could have. How about oh, here's one. Ice cubes. Okay. And let's say air. Okay, let's say they both start out at the same temperature, and let's say that that temperature is whatever it is in the freezer. Say down here someplace, -30. Okay, so somehow your house got down to 30 below inside. I don't know how. Let's just say it did. If we are going to heat both air and ice cubes, what's going to happen? The temperature is going to increase. So air increases very, very rapidly until it gets closer and closer, and then it evens out like that. Is this exponential decay? No. Is it exponential growth? Yeah, but it's growing from a negative from the bottom going up. We're going to see how that works later on. But here's ice cubes. Why do ice cubes have this flat spot when they warm up?
Until all the ice melts, it's 32 degrees.
Right. This is an ice cube, and from here, it's water. Okay? So there's a period of time in which the ice has to change to water, and after that, it can warm up again. But it will stay at 32 until all the ice has melted. Page 309. Let's see how to write this pizza problem. Down at the bottom of the page, it says the pizza temperature as a function of time is 70 plus 380 e to the negative, they say negative 0.11 t. Okay? Now I want you to notice where I'm putting the 380. Do you see where the 380 came from? It's how much the temperature of the pizza had to cool off, right? Did it have to cool all the way from 450 to 0? No, it only had to cool off until it got to room temperature, right? So up until now, our exponentials had a horizontal asymptote at 0. Now we have a vertical shift of 70. What did it do? It moved our graph up 70 degrees. So it started out at 380. All right. Now, they have this negative 0.11 t, and they have our growth factor as E. Does anybody remember what the value of E is approximately? E is about, what do you get, Laura? Oh, 2.7 something, right? So it more than doubles, right, in a certain amount of time. Now, if you notice here, it says negative. This negative sign here is for decay. decay is negative. So what do you think positive will be? Growth. Page 310. Let's graph it and sketch the graph. So, Newton's law of cooling. Got some pizza in the oven. Put in the graph here. Cools off from 450. And then I'm going to go, say, out 40 minutes. And I'm going to go from down to 0 for my horizontal axis, just so that you can see. And then I'm going to put in here y equals 70, just so that we can see that's our horizontal asymptote. So if you wait 20 minutes, there's only 50 degrees difference between your pizza and room temperature. You're like, yeah, it's kind of warm, but not really. If you wait a half an hour, it's not even, like the pizza is below room temperature. So when you put it into your mouth, it will like feel cold because it's lower than your mouth. So right about 100 is where you notice something isn't hot anymore. You notice it's cold. Sketch the graph. We did. Then it says, describe how the temperature of the pizza is changing every 10 minutes. So I'm going to draw the graph here. And we're going to put in every 10 minutes. So at 0 minutes, at 10 minutes, at 20 minutes, at 30 minutes. Here's my graph. How is the temperature changing? Does everybody agree this is how the temperature is changing? Change in temperature, temperature per change in time, which is the slope, right? The slope here is cooling rapidly, right? How does the cooling part translate in our equation or in our slope? It's going to be negative, right? How does the rapidly translate? It'll be a big number, like 30. It's losing 30 degrees per whatever. Okay? At 10 minutes, so the slope here, let's say, was 30. The slope here appears to be about 1, negative 1. What does that mean? Each minute, it's cooling 1 degree per 1 minute, right? Over here, what's the slope? It's like about a half, negative 0.5. Oh, I didn't put in the negative sign there. So what does that mean? It's cooling at negative 0.5 degrees per minute. So it's cooling slower and slower, right? And finally, negative 0.01 degrees per minute, or negative 0.1 degrees per minute. It's only going down by 1/10 of a degree per minute. Eventually, it will be going down at 0 degrees per minute. We'll do the math when we come back, just so that we can see how that works. Today? Oh, okay, thanks. So it is whether you smoke or chew. So it's not the smoking that, which kind of makes sense. I kind of figured that it was the nicotine.
Yeah, but it's interesting to know. Actually, that was the case of my grandmother too. She was drinking a lot of coffee.
Yeah.
At the end there. A lot of coffee.
One, to me, some of it is, I think some people have an addictive personality. You know, they have to be, they're compulsive about something.
Oh yeah, I think that's very true. I think would you, just based on your experience, would you say that everybody has something they're probably a little
Compulsive about?
yeah. I guess in the
No, I would think, you're thinking only of type A people. I'm thinking of type B people.
Mhm.
I know a lot of type B people that are like, yeah, I'm not going to get excited about anything, Kevin.
just one.
What do you think, Gavin? Do you think there are people that don't just can live their lives and not?
Well, I suppose there's people that really can.
I'd like to be more of a
More type B?
I just have a few things that I'm very, very type A about.
Like?
Workspace cleanliness. Like, everything needs to be organized and needs to make sense to me. Otherwise, I'll go out of my way, I guess, to,
Yeah?
I don't know, and it bugs me if people leave a mess.
Yeah?
Or at work. My room is a different story. I don't want to talk about that.
So you are intolerant of the faults of others, but yourself.
Well, it's just, I mean, other people don't frequent it, you know?
Yeah, that's
So
true.
Yeah.
So it's more like making sure nobody has to suffer with.
Yeah. It's like a living room. Like a living room should be, I don't know.
A cleaner space since it's shared by all.
Yeah, I don't know. But that's just my way of thinking. Not saying it's right or anything.
Is that Michael and Phil that are in Menominee?
Yep.
Okay. So in order to answer the questions on page 310, we're going to need to know some data points. Because we want to know, well, how is the temperature changing between 0 and 0.1 seconds? And then between 10 and 10.1 seconds. And then between 20 and 20.1 seconds. So we're going to have to complete this table to figure that out because we don't know what the value, or we need to know the value at each one of those seconds and 1/10 of a second later. So the way we're doing it is from this graph that we had, we're just taking a point and then 1/10 of a second later, a point and then 1/10 of a second later, a point and then 1/10 of a second later, a point and then 1/10 of a second later. So let's fill out each of those values. Let's do it in Desmos because that's an easy way to do it. So the first thing we're going to do is in Desmos, this is an important thing you can learn how to do that will make your life easier to answer test questions. Let's make a table. So add table. In this spot here where it says Y, now mine says Y3, yours will probably say Y1. We're going to put in the formula. What's our formula? Look at the bottom of page 309. 70 plus 380 times e to the negative 0.11. Now here's where the table will help you out. Our formula says to put t in there. We're going to write x3. Now I'm going to write x3. You probably will have to write x1 because is your first column x1 or is it, let's see here. See, mine says x3, so you have to make sure that you get the right letter in there when you do it, okay? So I'm going to put in my numbers. 0, 0.1, 10, 10.1, 20, 20.1, 30, 30.1, 40, 40.1. If you need some help, show me your Desmos and I'll see if I can help you figure out how to do it. Because it's important that you know how to do this. Yeah, and let's see. Do you just have to the negative 0.11? Or what do you have here at the end? It will show error until you get to the very end. X, you see, you just have X, so you have to write X sub 1. So, just, if you take out that print, yeah, just put in a 1 right there. X, 1. It just automatically puts in the 1. If you type a letter, then a number after it, it will make that a subscript. So, we can now fill in the table. 450. 445.8. 196.5. 195.1. 112.1. 111.6. 84.0. 83.9. 74.7. I'll say 74.67. 74.61. Madeline, do you know how to do that in Desmos? Okay. You guys are okay? Gavin, you got it? Menominee, you guys are okay? How to fill out the table? You guys got to talk again because I can't see you.
Yeah, we're good.
Okay. Man, I like that thing. I'll just hang up on Menominee. That'll learn them.
Can you hear us?
Yeah, no, that helped.
Okay.
Okay. All right. So now when we do the A of t, our A of t formula is this number, 445.8, minus this number. But this time we have to divide by 0.1 minus 0. So on my calculator, I get 445.8 minus 450, close parentheses, divided by, and I'm going to just put 0.1 because each one of these are 0.1 apart. So each time my number that I get is going to be one number apart, or 1/10 apart. So this is at 0, it's cooling, right? And it's cooling rapidly. And we would say negative 42 what? Degrees per minute. Now, I want you to think about the powerful nature that has. At this point right here, have we taken it out of the oven for a whole minute yet? No. We've only had it out of the oven for 6 seconds. Right? That's 1/10 of a minute. In 6 seconds, we've already been able to determine that it is cooling at the rate of 42 degrees per minute. And we just started. Okay? Let's go to the second one. 195.1 minus 196.5 divided by 0.1. One clear. Parentheses, 195.1 minus 196.5 divided by 0.1. Okay, how do people make mistakes? The first thing they will do is they will take 196.5 minus 195.1. That results in the number 1.4. What's wrong with 1.4? Makes it seem like the pizza is getting warmer, right? It's a positive number. We need the number to be negative. So you always have to take the second value, the new function minus the old function divided by the new value minus the old value. Okay, next one, 111.6 minus 112.1 divided by 0.1, negative 5 degrees per minute. Next one, well, I don't even need a calculator for this one. It goes down 0.1 degree per 0.1 minute, which is negative 1, right? So our slope at this point is a 45 degree angle going down. Last one, 74.61 minus 74.67 divided by 0.1 is negative 0.6. Oh, I didn't put in degrees per minute. So let's reiterate what's happening here. The pizza is gradually getting closer and closer to 70 degrees. The function looks like this, but the slope, let's do just the slope equation. It starts out negative 42 at the beginning. Then at 10 minutes, it's negative 14. Oops. Then at 20 minutes, it's at negative 5. Then at 30 minutes, it's at negative 1. Then at 40 minutes, it's at negative 0.6. What do you see is happening? It's increasing, right? Horizontal asymptote. What line won't it cross? The pizza is never going to warm up. Newton's law of cooling. The pizza is never going to warm up. That is an important law of thermodynamics. It's an absolutely crucial law of thermodynamics. Heat is energy. Energy in a system always decreases. It never increases. It always decreases. So I was teaching 10th grade algebra 2. And Gretchen's calculator wasn't working. So Barrett said, oh, just throw it on the ground. That's what I do with mine, and then it starts working again. And so she was going to do it, and I said, Gretchen, don't do that. That's going to make your calculator not work. It's one of the laws of thermodynamics. Everything gets worse. Well, they married each other. She's the school secretary. They probably have 5 or 6 kids. I don't know. He's a custodian at the university. But, the laws of thermodynamics, don't try to violate them. They will not work out in your favor. Page 311. So, we looked at the accumulation of drug in a person's system. Oh, by the way, while you guys were on break, Sam found that caffeine is negatively impacted by the nicotine in smoking. So it doesn't matter whether you chew or vape or whatever, it's the nicotine, which kind of makes sense because nicotine is a drug. Things that people don't realize that just amaze the living daylights out of me. High school kids don't realize that vaping contains nicotine. They're like, really? I didn't know that. Other things people didn't realize. When they put somebody to death, one of the drugs they give them is nicotine. Yeah, it'll kill you.
It's crazy.
It is. It is just absolutely phenomenal. So we're talking about a drug now, and it's an accumulation of a drug in a person's system. The model that we're going to use is G of T equals 60 minus 60 e to the negative 0.05 t. This is the amount of drug and this is hours. Okay. Up until last lesson, all of our exponential functions had a horizontal asymptote of 0. Last function, what was our horizontal asymptote with the pizza? 70 degrees, room temperature. This time, do we have a horizontal asymptote? It's an exponential function. All exponential functions have a horizontal asymptote. The question is it 0 or is it another number? Voting for 0, raise your hand. Voting for it to be another number, raise your hand. What's the another number? 60. This number here is the vertical shift. What's the question?
Nothing.
It's the vertical shift. How much drug does the person have in his bloodstream at the beginning? Well, if you look at this part here, this would have been 60, right? Everybody agree? It would have been 60. But what happened to our graph? It's shifted up 60. So our 60 that would have been at 60 is now down here at 0, which kind of makes sense, doesn't it? I'm going to give you medicine in just a few minutes. How much of that medicine do you have in your bloodstream right now? Nothing. Okay, have you ever watched a TV show about an emergency room where they'll come in and they'll say, okay, we need to give you this drug, but it is absolutely crucial that you have not used any heroin or opioid or something like that. Because when we give you this drug, it's designed to have the whole effect. If you've already got that drug in you, it's going to screw up what the drug is good for. So I need to know, don't be lying to me. I'm not trying to get you in trouble. I'm just trying to make sure that I give you the right amount. Have you ever seen those TV shows where they do that? And the person says, oh, yeah, I don't do drugs. And then they get an overdose or something like that. I don't know. I mean, they have different shows that do different things. So, this part here tells us
It's negative. There's decay.
very good. It's decay. It's decreasing. Since this number here is pretty small, it's going down slowly, right? But the problem is this is negative decay. So what's different about this lesson is this part right here. Why is that part different? Well, because remember this we just did in the last lesson, the 70 degrees. We understood how that impacted our formula. We know that we're dealing with an exponential function. We know that it's a decay, right, because of the negative. But now we've got a negative negative. Let's see how that graphs. First off, can you describe a different situation in which this function could be used to model the temperature of an object? What would it be? You take a frozen object out to thaw? Maybe that might be a spot. Okay. 2. The formula was originally intended to model a situation in which a patient is receiving a drug at a rate of 3 milligrams per hour. Body is eliminating the drug at a rate of 5% an hour. So let's draw the graph and see what we get, just so that we know what we're talking about. So we've got our graph. G of t equals 60 minus 60e to the negative. I'm going to put in y equals 60 and change the color so that you can see. Why did I put y equals 60 in there? Yeah, it's a horizontal asymptote. Good. So let's draw our graph. So we start out at 0, and we gradually get closer and closer to our horizontal asymptote. G equals 60. I don't know, 60 milligrams. It doesn't say what it is. Yep, milligrams. Part A. First, use the formula to calculate the average rate of change over the first 10 hours. So we're going to get, I'm going to put the t in the middle. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, let's use the formula and fill in that table. So let's go to Desmos and let's copy down the formula. So add a table and remember how to do it. We're going to put in 60 minus 60 times e to the negative 0.05. And my variable is x3. I don't know what yours is, but my variable is x3. Now I'm going to go through and put in all the other hours. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Anybody need help? Because this is really going to save you time when you get to your assignments and when you get to your test, being able to fill in that table in Desmos. So after 1 hour, obviously at 0 hours it's 0. So I'm filling over in next here. And 2.93, 5.71, 8.36, 10.88. What do you see is happening all the way along here? 5, it's 13.27, 6, 15.55, 7, 17.72, 19.78, 21.74, 23.61, 25.38, 27.07, 28.68, and 14 is 30.21. Now, that just gives us our g of t function. How do we find the a of t function? Take this number minus this number and divide it by 1. Or in other words, just take that number minus that number, right? So the first one is 2.93 something per something. What? Milligrams per hour. So at the very beginning, since it's positive, what does that tell us? It's increasing, right? 2.93 in the first hour. Then we've got 5.71 minus 2.93, 2.78. 8.36 minus 5.71, 2.65. What do you see is happening every hour? Yeah, it's still increasing, but it's not increasing as fast as it was before. So let's keep going. 10.88 minus 8.36. 13.27 minus 10.88. 15.55 minus 13.27. 17.72 minus 15.55. 19.78 minus 17.72. 21.74 minus 19.78. 23.61 minus 21.74. 25.38 minus 23.61. 27.07 minus 25.38. 28.68 minus 27.07. How do you know if your numbers are wrong?
If they're increasing.
Yeah, if they would increase or if you would get a decimal place moved over or something like that along the way. So as you go farther down, the rate of change in milligrams per hour, it is always positive, but it keeps getting closer and closer to 0. Page 312. For part B, they're asking for something different. They're asking for an iterative change. Iteration means the next computation is based on the previous one. Here's the iterative change they're suggesting for part B. Now it says, assume 3 milligrams is being added to the bloodstream and 5% is being eliminated each hour. Okay? So, in hour 0, we are going to add 3, but then it says subtract 5%. So our iteration is add 3 minus 5%. How can we numerically do that easily? Add 3 and multiply by 0.95. Would you agree that's subtracting 5%? So 3 times 0.95 is, so at 0 we have 0. After 1 hour we have 2.85. Plus 3, close parentheses, times 0.95. Oops. I have to put in the parentheses first. So, there we go. And we get 5.56. Parentheses. Second function answer plus 3 times have to close my parentheses, times 0.95. Parentheses. No, it won't let me do plus. I have to do answer. Plus 3, close parentheses, times 0.95. Do you notice the relationship between these numbers and the numbers that we did from our formula? Do you see how they're kind of the same? Now, it's probably not exactly 5%. That's probably part of it. But the other part is that the 5% isn't just subtracted at the end. It's subtracted all the way through the process. One of the problems that you run into with iterative calculations is that if you skip a step, you got to start all over again.
I don't understand this. So you're adding 2 so the first one, for example, it's 2.
Okay, I'll get you caught up. Take your calculator. 3 times 0.95 is?
2.85.
Did you put that down someplace?
No.
Okay, now, some parentheses. Second function answer. So it's going to take this number, add 3, close parentheses, times 0.95. Okay, so if you want to get caught up and you want to continue from where we are, at this point right here, in row 7, type, 17.19. On your calculator, type this whole thing in here. I'll zoom in a little bit. Does that help if I zoom in? So I'm going to type 17.1, oops, I should have put in parentheses first. Parentheses, 17.19477.412 plus 3, close parentheses, times 0.95. Parentheses, second function answer, plus 3, close parentheses, times 0.95. Parentheses, second function, answer, plus 3 times 0.95. Now, there is a way to do this in a spreadsheet that Desmos can't do. And I wish I could figure out how to get Desmos to do it. But if you have time and if you have amount, you start out at 0, and then you take equals this number. Oops, I have to put in parentheses. Parentheses, this number plus 3, close parentheses, times 0.95. So the iteration is a lot easier in Excel because Excel is able to use the value. Oops. So then this value here is this amount, oops, parentheses, this amount plus 3, close parentheses, times 0.95. I screwed up on the first one. I should have just said equals 3 times 0.95. So if you notice, once I do that, I can just drag that whole thing down for 14 rows. Uh-oh. I didn't drag this part right. Drag the whole thing down for 14 rows, and it'll give me all of my calculations because each row here is based on the previous value. So I'm just going to fill in the rest of them here and show you that 11 is 26.2, 12 is 27.74, 13 is 29.2, 14 is 30.59. So I graph those in Desmos, and I show you here that over that course of time, my green function, that was the exponential function, is really close to the dots that I made for each point. Now my dots skew off a little bit as time goes on, and so my 5% kind of catches up to me. They probably should have said something like 5.1% or something like that. I don't know. It's off by a little bit. Either that or else our exponential function, instead of being negative 0.05, should have been something like negative 0.06 or I don't know, something like that. But the reason that it's different is because your body is eliminating that 5% every single second, whereas our calculation is only eliminating it at the end. So it's not going to be eliminating as much as your body is eliminating. Page. (313) did a lot of work to show you that those two functions are pretty much the same. One of the competencies that we have in this class is to talk about iteration, because when we get to the calculus, we spend a lot of time on sequences and series and how they affect the growth of something. And we have to be able to model a sequence and a series. Like, for instance, there's a way that you can figure out pi using this iterative process. There's a way that you can figure out e using this iterative process. So we just go through those in the calculus, and they wanted to show you that in this lesson. But the other thing that they wanted to show you is that if you have a negative decay, it's going to be a decay model flipped upside down. Page 315. In terms of effectiveness and safety, what factors should a doctor consider when prescribing a drug? Want to make sure you give them enough. Want to make sure you don't give them too much. Okay? Those parameters are listed here on this page for this particular drug. A team of doctors is evaluating the effectiveness of 2 experimental drugs as a result of clinical trials. Here are the 2 things that we're going to compare. We're going to compare y of a as a function of time is 7.71 times t times e to the negative 0.74 t. So in other words, we're going to graph this. The other one we're going to compare is on the next page, the table. Which starts out, this is drug B, T, and then Y sub B is also as a function of time, and it goes 0 is 0, 0.2 is 2.28, and so on. We're going to compare those 2 functions and answer these questions about them. Here are the 3 requirements. Where'd my purple pen go? Requirement 1. Not more than 4 micrograms per deciliter. In other words, the function never goes above 4. 2. Relief in 0.2 hours. And then 3, relief for at least 3 hours. So you're going to use the table to answer those questions for drug B. You're going to have to graph it, graph the function for A. So here's my graph of the function A. Oh, maybe not. That doesn't look right. There it is. I have to turn some stuff off here. Okay, so answer those 3 questions about those 2 graphs. Go, and I'll give you some help as you go through it. I think it's easier to start on the table. So here's the 3 questions right here. Does it ever exceed 4 micrograms per deciliter?
No.
It gets pretty dang close though, doesn't it? What time?
0.8.
Yeah, so it gets really close at 0.8. So does it meet requirement 1?
Yeah.
We're on drug B though. Yes. Okay. 2. Does it look like by 2 hours or 0.2 hours it's at effective pain relief. Now you have to know what number effective pain relief is. If you look back at the previous page, it says it's effective if no, maybe it's not on the previous page. There it is. Greater than or equal to 2 micrograms per deciliter. So does it provide 2 micrograms by 0.2 hours? You done with the first one, or are you just working on the second one first?
No, I don't even know what I'm doing.
Okay. Well, I like your graph. Okay, here's the 3 things. It can't go over 4. So does A go over 4? No, not quite. Okay. Does it get up to 2 by 0.2 hours? So I would write y equals 2. And then put your dot on, or click on your dot to see.
Where's the first one?
So does it reach 2 by 0.2 hours? No, it doesn't get to 2 until, no, because, oh, no, it doesn't, this one is yes. It doesn't exceed 4, right? It doesn't go over 4. Yes, it doesn't go over 4. So I would write, yes, it doesn't go over 4. And then for number 2, it doesn't reach 0.3 or 0.2 until, or it doesn't reach 2 until 0.33 hours. Okay? And then you have to do the same thing for this table. Just use the table values the same way. Marlena, you okay?
Yeah.
You good? No? Maddie?
Yes.
You have to graph that second one. How you doing, Eric?
Not too bad.
Gavin, you getting it? You want
Yeah.
some help?
No, okay.
Got it? Nick?
I'm good.
Menominee? And thumbs up. Anybody need some more time? Okay, so when I graph A, I did two things here to show you what's going on in this function. The blue, I have the blue set so that it starts at 0.2 hours because we want it to be effective from 0.2 hours. And I have it go all the way over to 3.2 because what has to be true? It has to knock you out for 3 hours. So I have that part. The green shows the window from 0.2 to 3. The blue here shows from 2 to 4. We don't want it to ever have any more than 4, and it won't be effective until it gets more than 2, right? So, a couple questions that we know about drug A. A lasts long enough, correct? It doesn't get too high, correct? But it doesn't start until 0.3 hours, so 18 minutes. It's not effective for 18 minutes. That's not acceptable if you've got a migraine, right? I want relief and I want it now, right? Okay. Drug B. Did anybody have no for the first answer? Can you see why somebody would say no for the first answer? So I think it's kind of important. If you look here at the table, at 0.8, you're at 3.98. At 0.6, you're at 3.93. And at 1, you're at 3.77. So here's the 3 points that we know. But is it possible that the graph would say before this one come back down through 3.98? In other words, that this peak would have been over 4? Or is it possible that it would have gone like this, gone over 4, and then come back down to 3.77? Because we don't know every single step along the way, we aren't sure what that is. Is there a drug that we could tailor make for this entire process? So I was talking to a lady last night who is a salesman for Janssen Pharmaceuticals. Janssen is a subsidiary of Johnson & Johnson. They make ecstasy for PTSD patients. Why? The great crippler of our returning vets is PTSD, right? Suicide rate is higher than the casualty rate was in Afghanistan or in Iraq. Suffering PTSD, Janssen, which is, like I said, of Johnson & Johnson, made a drug that's like ecstasy that they can prescribe to patients to help them get over post-traumatic stress disorder. On this page, it asks us to make a drug that is effective, so it has to at least go through this point. It can't cross this line. And it has to at least be as long as this. Now, it could be wider than this green area, but it has to include all of that green area, and it has to be not above the 4. So I put in some numbers here for this formula to try to show you, can I do it? Well, if you notice, I can get really close to that first one, but keeping it so that it doesn't go over the second one, you just have to keep playing with those values, and I just